All right, today let's look at how to do adaptive remeshing inside Ansys Mechanical. And out of laziness, I'm not gonna do dyna this week because it's holiday, but I will do dyna next weekend when the holiday is over. All right, so the process for remeshing is actually extremely simple. I'm basically dividing this topic into two videos instead of one. I usually would have done this as part of the dyna video because I want to use this as a baseline because but I'm out of time, so I'm not gonna do this over the holiday. So I'm just gonna present it. For mechanical by itself, then I'll do dyna in the next video to summarize to sort of complete this topic. Okay, so for mechanical, it's actually really easy. They've made it super easy for us, right? So basically, there's an energy-based method, and there is a mesh-based method. The energy-based method is basically looking at a string energy, and then there is a coefficient right here. This coefficient is basically fits into here. Essentially, if you look at the total energy and you look at the string energy on a single element, if that falls below some threshold, then you remesh that element because the element has been essentially deformed by a significant amount. So the smaller this number is, the more of the total body's mesh you're gonna remesh. It's not really easy to control or visualize, which is why I only use this when I know there's a lot of bulk responses. Like for example, in like a forging, I would do something like this to use energy-based system because I know whole body is gonna deform a lot. And then the string energy is basically defined as such. It's a lot, but basically it's looking at the different string components and look at the volume of your element, and then that's where you calculate the total string energy of the element. Just think of this as how much the element is gonna deform or stretch in terms of volumetric component. There's also a mesh-based method, which is really defined based on a mesh skewness and Jacobian ratio. Right? Skewness is basically how much the element itself has deformed in the initial configurations. So this is usually represented by some kind of nodal movement, as you can see here. And this is the threshold. Usually you check the mesh skewness for mesh quality check, right? Now there's also the Jacobian ratio, which is really a degree of deviation from a perfect shape. So when you have a perfect shape, you have a zero Jacobian ratio. Otherwise, you're gonna have higher and higher Jacobian ratios because the element has become highly distorted. So if it's above 0.1, usually we'll just remesh it. This is another measure of element distortions, essentially, right? So both of these are basically just looking at each of the single element characteristics. So this is, in my opinion, is much more useful in an O-ring compression type of analysis because in an O-ring compression type of analysis, yeah, you do have a lot of bulk responses, right? But also the area where the contact occurs is actually going to be really critical. So if I were to hide this to show you real quick, you can sort of see that this area where the contact occurs is actually really important for convergence. So that's also where we'll actually want to mesh it a bit better. Obviously, the way I set up my mesh ratio is I actually remesh it a lot. This is a 60% O-ring compression that you're seeing here, right? Which is give you a pretty good. But let's run through what this model is, right? So I have two steel plate, basically two steel plate and an O-ring in the center. This O-ring in the center is basically just being compressed by 60% strain. This is a 5 mm gap. I'm compressing it by 3 mm, right? So quite a bit of compression on an O-ring. Then I have a nonlinear adaptive region assigned to the body, and then the skewness and the Jacobian ratio is assigned as such. Now this right here is really important. How often do you want to check for remesh, right? So you want to put this number not too high or not too low. It takes some little bit of a play around to see. But basically, if you set to 100, it's gonna do every 0.02, 2% strain, every 2% sort of the compression is gonna generate a remesh check. You play around with this number a little bit, you get a decent result. If you remesh too often, you actually get a worse responses. It take a lot longer to solve, and it's gonna give you a worse response because sometimes you don't actually need to remesh that often, especially when contact is involved, right? Like this. Another key thing to remember is that when you're doing automatic remeshing or adaptive remeshing, you have to do contact with the body selected. If you select the surfaces, right? If you were to select a surface as your contact pair, it's not going to work because the surface has to be the remesh has to encompass all of the contact elements. So you want to assign body to the contact pair instead of using surfaces, right? Otherwise, it's pretty basic. As you can see, once it's set up, I basically have this type of response, which is, it basically remeshes as it deforms to maintain element quality, right? So you get a pretty decent element quality. I can also check reaction forces on my fixed support, right? I haven't checked this, but you can sort of check it. It should give you a hyperelastic compression curve, which is like exponential growth, right? Look like that. And something like this is that if with enough computing power, I actually couldn't do more. I was gonna do even more than this much compression, but my student license ran out of element count, so I couldn't go any higher here in my home computer. But basically, this is the type of response you can get. This is extremely important when you want to compress a body into a high amount of tension or compression, right? It's very, very important to run this. Otherwise, you're going to get element distortion problems. You basically want to generate a rematch condition such that the element, there's a couple error messages you can sort of see inside here where it says, yeah, you see this element become highly distorted message, right? This has to go away as much as possible through the remeshing. So every time this happens, you want to make sure the rematching kicks in to fix it, and it does. Every time it kicks in, the rematching kicks in to fix it, and so on and so forth. This is how you know the rematching is going to work. And this is how you do a nonlinear adaptive region inside Ansys Mechanical. This is extremely easy. In Mechanical, they made it super, super easy. In Atlas Dyna, it's going to be a lot more interesting because in Atlas Dyna, we can actually do explicit analysis and do other type of analysis that Ansys Mechanical cannot do. But Ansys Mechanical has a very good nonlinear adaptive region capability. It's been around for a while now. It's very, very capable, very, very robust. Certainly a very good feature they have. Okay, thank you very much.